Hi guys, today we're going to take a brief look at the HC-SR04 ultrasonic distance measuring module. It's nice and simple to use, doesn't require any library installs and can be used in projects such as motion detection, parking sensors, robotics and such like. It's basically got a 4-wire connection. We have a ground pin and a VCC pin, which is the power supply for the module, which is 5 volts. We have the data pins, the trigger, which is an input into the module, and the echo, which is an output from the module. The trigger pin is set high and then low. Ultrasonic sound is emitted from the sensors. The echo is then returned and timed, and the echo pin is set high and then low and stays high depending on the distance of the object. So let's take a look how this works. The trigger pin is set high and then low. Ultrasonic pulse is sent, echo is timed, and the echo pin stays high depending on the distance. Here the object is slightly closer, the echo pin is set high and then low for a shorter period of time. So, as we can see, we're breadboard friendly, which is a good thing. So let's get wiring. First of all, we'll connect our power supply. So we want a black wire for our ground pin. We want a red wire for our VCC, which is basically our power supply to the module. We're going to use a white wire for our trigger. And we're going to use a blue wire for our echo. So let's take a look how we connect these 4 wires to our Arduino. The 5-volt supply on the Arduino is perfectly adequate to supply voltage to this module, so we can plug the black wire to the ground pin. We can plug the red wire to the 5-volt pin on the Arduino. So that's our power supply sorted. We're going to use pin 2 as our trigger, which is output from the Arduino, and we're going to use pin 3 for the echo, which is input into the Arduino. So there are our 2 data wires, there's our 2 power wires, and we can now power up our Arduino module and get coding. Okay, first thing we need to do, launch our Arduino environment, and depending on what version you have, you should be presented with a blank sketch as soon as it opens, which we have here. It consists of a setup area, and anything between these 2 braces here is run once as your program boots, and there's the loop area here, and anything between the 2 braces there is the main body of your program, which repeats over and over again. If you don't get a blank sketch when you open your Arduino software, in File Example Basics there's a blank sketch there called Bare Minimum, which is essentially where you need to be starting with. So, first thing we need to do in our setup area is we need to define the trigger pin as an output and the echo pin as an input. So to do this we use the pin mode command, open brackets 2, output, which is going to be our trigger pin. Here we go, trigger, which is our white cable, and then we need to set our echo pin, which was pin 3. So again we use the pin mode command, pin 3, which is an input, and that is input into the Arduino, which is our echo pin, which was the blue cable, if we remember rightly. And for the time being we're just going to use the serial monitor to display the output. So if we just use serial.begin and then a baud rate, we're going to use 9600, and that basically initializes the serial communication, which is where we're putting our output. So let's have a quick recap of what we need to do. We've got the trigger, which is output from the Arduino input into the module. We need to set that high for 10 microseconds, and then you'll receive a sonic burst from the module of 8 40 megahertz pulses, and then the module will set the echo pin high according to the distance of the object. So it sets it high, stays high for a length of time depending on the distance of the object, and sets it low again. And the distance in centimeters here is calculated by the time that the echo pin was high for in microseconds divided by 58. So as far as our variables are concerned, we need to measure the time when the echo pulse went high and measure the time when the echo pulse goes low, and subtract one from the other, and the distance is then calculated with that simple formula. So let's set up a few variables. So the first variable we need to set up is our time start. We're going to use unsigned integer, so unsigned int, because we're not dealing with negative numbers. So we're just going to call that variable time start. And then our time finish variable, again we're going to use unsigned int because it's not going to be a negative number. So unsigned int time finish. And then our distance again is going to be an unsigned int. We're just going to call that distance. And that's basically the 3 variables we need for this simple calculation. So if we go to our loop, within our loop area here, this is where we can start coding. So let's have a look at the first thing we need to do. First thing we need to do is set the trigger pin high. So quite simply, all we need to do there is digital write, and then pin 2, high, and that is as simple as that. Digital write, and then the pin number, and then you either use high or low. At this point we want to set it high, so digital write to high, which will set the trigger pin high. So next thing we need to do is just to give it a little pause, a pause of 10 microseconds. So what is handy? The Arduino has a useful little piece of code to do all your timing for you, and it's simply called delay microseconds. And in brackets we just need to put 10, and that will cause a delay in the program of 10 microseconds. All the timing's done by the Arduino itself, so we don't need to worry about that. So we've delayed for 10 microseconds, and the next thing we need to do is set the trigger pin low. So we need to do another digital write on pin 2, which is our trigger pin, and this time we just type low, and that will set the trigger pin to low. So we've pulsed our trigger now. We've set our trigger pin high and low. The module will then send its sonic burst out and measure the time it takes to receive the echo. The next thing it's going to do is it's going to set the echo pin high. So we need to wait until the echo pin goes high now. So to do this, we're going to use a while statement. So if we use while, and if we read the value on the echo pin, so we're going to use digital read pin 3, and then while digital read 3 is low, so all the time that the echo pin is low, it will execute all the commands in between these two braces.
which it doesn't need to do anything, so there's going to be no code between the two braces. So basically that little section of code just waits until the echo pin goes high. So all the while the digital read pin 3 is low, it does nothing. So we've waited until the digital pin has now gone high. So as soon as it goes high, what we need to do is take a measurement of the time. So it's now gone high, so it's dropped out of between those two braces of doing nothing. So we simply assign time start, which is our time start variable, equals micros. Now micros is a timer that just runs constantly on the Arduino. So we've assigned it the value of whatever micros was at the time, and the next thing we need to do is to wait again until the echo pin goes low. So we're going to do the same as before, while digital read and then our echo pin, which is pin 3, but this time all the time it's high, we don't need to do anything. So while digital read 3 equals high, we do nothing. So basically we do everything in between these two braces over and over again all the time that the echo pin is high. So basically we do nothing. So there we go, we're waiting for the echo pin to go low this time. And then once it's gone low, we drop out of these two braces, and then we can assign our time finish to the timer. So time finish equals micros. So we've now got a time start when the pin went high, and now we've got a time finish when the pin went low. So we've got those two times. If we subtract one from the other, we'll get the time, the length of time it was high for, and if we divide that with that simple equation, we can calculate the distance in centimeters. So with this simple formula, we use distance equals time finish minus time start, which is basically the length of time the pin was high for, and then divided by 58. And that will give us our distance in centimeters. And then all we need to do is to print that onto our serial monitor. So serial.println, which is print a new line, distance, which is our variable that we've put the distance in. We just need to delay a little bit before each reading, so I'm going to put a small delay in there using the delay command, and that simply gives the module a little bit of time to settle. So that's a delay of 50 milliseconds there, which is slightly different than the command we used earlier. So if we save that, make sure we've got that saved. We call it Ultrasonic 01, and then if we just check that our port is set correctly, and we can upload. All being well, we don't get any nasty red error messages. And there we go, successfully uploaded. So if we run our serial monitor now, we should see the results coming up on our serial monitor. And there we go. Now, if we look, I've set up our little web server matchbox again, and if we place that at different distances along there, you'll see the distance reflected into the serial monitor there. Here we go, we can see both screens there. So that's 5 centimeters. Move it along to 10 centimeters. You'll see the serial monitor, we've got a 10. 15 centimeters. And it's accurate supposedly within 2 or 3 millimeters. The smallest distance is reported to be 2.45 centimeters, but that's measured down to about 2, and it will measure up to approximately 4 meters, although you do lose accuracy over these sort of distances. Okay, so we've looked at how to access the module, and we've output some of the data onto our serial monitor, but how about if we wanted to output the data on something like this, which is an analog moving coil meter. This one's got a scale on it between 0 and 30. If we take a close look at the pins on our Arduino, we will notice that pin 3, 5, 6, 9, 10 and 11 all have these little wavy lines beside them. This means they support something called pulse width modulation, which is a method of simulating an analog voltage output on a digital pin. Now I've connected my oscilloscope and a digital voltmeter and an analog voltmeter onto pin 11 here. And so if we take a look at that, this is showing a digital write low onto pin 11, which is showing 0 volts on the oscilloscope, 0 volts on the voltmeters, a digital voltmeter, analog voltmeter. If we do a digital write high, that is 5 volts on the oscilloscope and 5 volts on the meters. Again, low 0 volts and high 5 volts. Back to low again, 0 volts. Now if we rapidly change between a high and a low voltage, here is a 25% duty cycle. It's high for 25% of the time and low for 75% of the time. We get a voltage of 1.25 volts. It changes between high and low several thousand times a second to produce this voltage. If we increase the duty cycle to 50%, as we can see, 50% of the time it's high, 50% of the time it's low, we get a voltage of 2.5 volts. And again, if we increase the duty cycle to 75%, it's high for 75% of the time, low for 25% of the time. The voltmeters read 3.75 volts approximately. And here we've got a duty cycle of 100%, which shows 5 volts, which is the equivalent of a digital write high. And here we see a gradually increasing duty cycle and the voltage on the meters gradually creeping up. So how do we utilise pulse width modulation within our Arduino code? Well, quite simply, we have a useful command called analog write. And if we do an analog write of 0, we'll have a duty cycle of 0%, which will in turn give a simulated voltage of 0 volts. If we do an analog write of 255, which is the maximum value we can write, we'll have a duty cycle of 100%, and a voltage of 5 volts. If we do an analog write of 128, we'll have a duty cycle of approximately 50%, and we'll have a simulated analog voltage output of about 2.5 volts. So there we are. Now I'm just going to assign another variable, unsigned int range, where I'm going to store this analog value, and I'm also going to set pin 13 as an output, where I'm going to attach an LED to that pin. So pin mode 13 output, and the idea is that the LED will illuminate when the distance gets above a certain value. So we're going to use an if then else statement to ensure that the distance doesn't go above a certain value. We want it to be not to go above 30 because that's the range on our analog meter. So if distance is above 30, so if that condition is met, open the brace, distance equals 30 and digital write 13 high. This basically ensures that the distance doesn't go above 30, and if it does, the LED is illuminated. So we'll close that condition with the closing brace, and then we're going to use else. So if that condition isn't met, then digital write 13 low, so we'll ensure that the LED isn't illuminated. And close that with the closing brace. Now we want to scale our distance that we calculated. Remember, distance is going to be a value between 0 and 30 now. It won't go above 30. But we want to map that onto our range variable, which is for our analog output. So the range is we want to be between 0 and 255. So we're going to use the map command, which will scale the distance variable of 0 and 30. So the distance we're expecting to be between 0 and 30, and we want to scale that onto our range variable, which was between 0 and 255. So that command basically scales up the distance, which was between 0 and 30, onto our range, which was between 0 and 255. And then we're going to just do an analog write to pin 11, where we've attached our meter, and the variable we want to write, which is range. And it really is as simple as that. We're going to just upload that. And if we look at the results here, that's our analog output, and the LED you can see below the ruler there is illuminated because it's effectively above 30. So if we put an obstruction in front of our module, we can see the analog meter at 10 centimeters indicating approximately 10, 15 approximately 15, 20 centimeters, 25 and 30, and if we go above 30 centimeters, the LED illuminates. So that just about covers the basics to get you started with this little ultrasonic module. We've had a quick look at the Arduino digital read, digital write, and using pulse width modulation with analog write. We've looked at scaling values with the map command. So I hope you found it at least a little bit useful and you can utilise some of the techniques in your projects.